Hey, how's everybody doing? So today we're gonna talk about Gauss's law. Um, this is one of the most important things we're gonna cover this semester, in my opinion. Um, this is like on par with Newton's second as far as importance go. I've heard it referred to as the Newton's second of E&M, not because it relates a force to an acceleration, but just because of how important and prevalent it is. So Friedrich Gauss existed from 1777 to 1855. Pretty good life for back in the day. And so what he did is he came up with a law that relates the electric field, right, the E field, at points on a closed Gaussian surface, which we'll explain that in a second, to the net charge enclosed by that surface. Right, and so we'll get into the Gaussian surface in a bit. First, I want to talk about flux a little bit. Right, and so one of the ways I like to imagine flux is to think of like a stream, right? So I guess that is a pretty good color for a stream. And so let's say you have a stream. Maybe you have a velocity field instead of an electric field for the particles in the stream, right? We're not going to get too into field theory. But so let's say we have some kind of a stream, and we're going to take some kind of a surface, right? And so let's say we take this surface. Oh, wait, can I? Oh, I can't rotate. That would have been so perfect. Oh well. Right. And so if we orient our surface so that the area vector, right, which points perpendicular to the surface, right, and you can have it either, up or down. I should probably go with down, actually, now that I'm thinking about it. Oh, Lord. All right, and so if we have it like this, we can see we're going to get as much of this stream going through here as possible, right? If we were to take the exact same setup, and maybe now we take our ring and we orient it like this, right? Now we have area vector perpendicular to velocity. All right, we can go ahead and be super good note takers and makers. Right, and so we find that the flux goes to 0. Right. Here's a symbol for flux. Is a capital phi, I believe. And so if we get the maximum value when the things are pointing in the same direction and the minimum value when they're perpendicular, we can use a cross product, dot product. Off to a 6 start. Or we can say the flux is equal to AV cosine theta, where theta is the angle between A and V. Right, and it's a dot product, not a cross product, so the order doesn't matter. You get a scalar as the result. Right, this should be slightly reminiscent to when we had work is equal to F dot D, right? If you have a block and it's traveling in this direction because you're applying a force, right, you get a higher network than if you were, let's say, applying the force at an angle, and then you would get no force no work if you're applying the force straight down, but it moves to the side, right? And so that's why we had like normal forces typically don't do work and things of that nature. Okay. So there we go. We have a pretty good working definition for flux now. And as also, we can go back to our stream example briefly. Right, and just as you can imagine, right, if you were somewhere in between the two cases, right, you're going to get something in between the max and zero flux, right? Right, and that's just because as we change theta, right, we change the value of the flux. So that's flux in a nutshell. Okay, and so now let's think about the flux of an electric field. I guess if we want, we could say, like, hey, this is 23-2 and 23-3. Right, and so the flux of an electric field, right, which we are going to abbreviate to E field. Later on, we'll have a magnetic field as well, which is the B field. Great choice of letter B. When you think magnet, you think B. But there's M fields and stuff in other things. Right, and so I'll always specify when we're talking about the electric field as the E field, just so we kind of know what's going on. And so let's imagine we have, let's say we got a positive charge. Why not? Right, a little bit of point particle. And so we're going to introduce what's known as a Gaussian surface, right? And Gaussian surface, we're going to use for this, let's call it a sphere. All right, and so if we were to draw the electric field lines from this charge, it's a positive charge, so they all are going to point radially outwards. And and they go into the plane, out of the plane, right? Just for simplicity, I'm only drawing 2D fields. And so it's important to keep in mind that the electric field doesn't only exist where you draw the field lines, right? Field lines are a visualization of the strength of the magnetic field, where the closer they are together, the stronger they are. But as you can imagine, if we tried to draw everywhere the electric field is, we would just be filling in everything. And like, what are you going to do with that, huh? Nothing. Right? And so the electric field is everywhere, but we just draw it in certain spots. And so, right, we chose a spherical shape because the point charge has spherical symmetry. Right? If you take a point charge and you rotate it, you spin it, you turn it, you do whatever, you look at the back of it, it's identical everywhere, right? It's spherically symmetric. You know, you can take a sphere and you can, you know, rotate it as much as you want and it'll never look different to you, right? If you were to take a cube and turn it a little bit, you go, oh my God, I'm looking at an angle now, right? There's no such thing as like looking at an angle for a sphere, right? I mean, let's not get into like the philosophy of what it means to be at an angle, but like in general, it's you know, uniform. Y'all know what I'm saying. And so what we get from that is that everywhere along this surface, right, we get the area vector is going to be pointing out. And the electric field is pointing out. And so we have everywhere along this sphere, we get the area vector is parallel to the electric field, right? And as we saw, well, I guess area parallel to V gives us the max, right? And so what's going to happen is if you have right, maybe the electric flux is A E cosine theta, right? Well, theta is going to be 0 everywhere. And so cosine theta is going to be 1 everywhere. And so you get the total flux is just AE, right? So the area of the sphere, 4 pi r squared, times the electric field. And here, since it's a point charge, we know the electric field has a value of kq over r squared, right? And so if our Gaussian surface has, I totally clicked a different color marker. And so if the Gaussian surface has some radius r, right? And so then all of a sudden we have, right, 4 pi r squared times kq over r squared. And so we just get a 4 pi kq as our flux. Cool. And so, right, the first kind of example we picked something that's very nice, right? But the real world is terrible. No, it's pretty cool. You know, isn't always like that. Maybe now let's say we have 2 charges. Right, and let's say, you know, we draw some kind of potato-shaped Gaussian surface. Right, already you can see how things are much less nice, right? And so you have, well, field lines that are going to be pointing out. Well, right, maybe something like that. And so already you're not necessarily having everything be perpendicular, right? You can see if we look specifically like right around here, we're coming in at an angle. Here we're at an angle, right? And it's you know, not going to be as easy to deal with. And so if you have a situation like that, right, you would have the electric flux is equal to the closed integral of E dot dA, right? And so where we had initially, right, just dotting the two. Now we're going to integrate around the area, right, which as you can imagine, this is going to drastically increase the complication of this problem. And we haven't even considered, right, what would happen if we dropped a negative charge in there, where now we have the field lines pointing inwards, right? Right, and so it's things do get drastically more complicated with the way the geometry changes. For this class, we will always have a convenient symmetry when we do a Gauss's law problem. It's kind of an ugly shade of green. No offense, but right, while this might not be true in some of the upper level courses, for now, right, we're always going to have some kind of a useful symmetry. And typically in that symmetry, what we're going to do is have E parallel to DA. Right? And so what that does is if you have E dot dA, where E is parallel to dA everywhere, then what you can do is have this be equal to this. And the electric field's almost always going to be a constant at our Gaussian surface. And so we pull that out, and we have E times the surface integral of dA, right? This, of course, is just equal to A. And so we get that the flux is almost always going to be equal to just EA, right? This is the beauty of Gauss's law, is that now it takes something where we would have to integrate around this surface for the flux, and it just goes find the electric field, well, or just leave it as E, right? Oftentimes you're solving for the electric field and you use Gauss's law, and so you just leave it as E, right? And then you find the area of the Gaussian surface. And so the most common Gaussian surfaces we're going to deal with is a sphere, which has area sphere is 4 pi r squared. We could also have a cylinder. And so here's where it starts to get a little tricky, because you only want the area that's going to be has the area vector parallel to electric field. And so if we were to say have a line of charge, right, maybe this is a bunch of, plus q's, right? And so let's say it's semi-infinite, right? So it goes on for very far, right? And let's say if they're all positive, the electric field is going to be pointing out everywhere, right? Same on this side. Ooh, look at that. All right, and so if we were to think of a Gaussian surface, what did I use before? I used like bluish. I think I used pink actually. All right, and so our Gaussian surface for this could be a cylinder, right? Where we have the electric field going through that surface everywhere, right? And it's going in and out of the board too, again, three-dimensional. And so here, right, what's the area of a cylinder? We have pi r squared at the top. Pi r squared there. And then we have, well, let's say we have some height h. No. We have some height h. All right, go ahead and label everything r. And so then we got the area for the top and bottom, right, the caps of the cylinder. And so now the outside is just going to be the circumference times the height, right? If you imagine you take that circumference and you just move it all the way down, you have 2 pi r h, right? And so in each case you have r squared, length times length. You get some SI units of meters squared everywhere, which is good if you want an area. And so we can say the area of a cylinder is equal to 2 pi r squared, right? 1 up here, 1 down here, plus 2 pi rh. But the electric field is only going through the side of the cylinder, right? So if we do E dot dA, it's going to be, well, we can call the top, we'll call this area 1. By symmetry, the bottom's also going to be area 1. And then we can say the side is area 2. And so we could do E dot dA1 plus E dot dA2 plus E dot dA1 again, because there's 2 of them. And we see the area vector sticks straight out. And so the area vector is going to be perpendicular to the electric field for area 1. And so we get these both go to 0. And so the only surviving component is from the outside. And so when we talk about the area of our Gaussian cylinder, oftentimes we are just going to have the area two pi rh. And we'll see some of this in some practice problems. Okay, and so what Gauss's law actually says is epsilon naught times the flux, I'm going to put an E down there just so we know, is equal to Q enclosed, right? This right here is Gauss's law. Right? And then 90% of the time, we're going to go ahead and substitute in the electric flux is equal to the surface integral E dot dA. And just so we're clear, anytime you have an integral sign that has this little circle in it, right, that looks like the super fancy math symbol, that just means it's a closed loop, right? And so, you know, what's going on there is, you know, if we have our positive charge, we have our Gaussian surface, like this has to be a full surface, right? I can't come in and say, here's my Gaussian surface, I'm cutting a hole out of it, right? That doesn't make any sense. You know, I also can't do something real wonky and just be like, oh, like my Gaussian surface is something like that is closed. It's hard to draw a non-closed loop. I guess just that, right? You can't do something like that. It has to be a closed area. All right, and so like even though we lose the tops and bottoms of our cylinder when we do this, we still have a closed area we're integrating from. And the whole idea there is there's no way any of the E field is sneaking out unaccounted for, right? You have to fully encompass it just to make sure you get everything it's doing. Okay, and so when we combine these together, we get the form of Gauss's law we're going to use the majority of the time. Epsilon naught times the integral E dot dA is equal to Q enclosed. Okay. And let me see where we're going to go. So let's go back to a point particle. And what we're going to do is try to find the electric field due to a point particle using Gauss's law. Charges are yellow, the color of electricity. Sure. And so just we can go ahead and we can say we already know the answer, right? For an electric field, we have E is going to be 1 over 4 pi epsilon naught Q over R squared, right? And then, you know, we can vectorize it. But here we're going to be solving for the scalar, right? Just because you have the dot product, you get a scalar out. And then this is one of the kind of things that is where you start following like what's physically happening in the system as opposed to just blindly following math, right? Because you could get, maybe you know, it's pointing in R hat, or it could be pointing in I don't know, some other direction where you have to like physically then go on and add the vectors at the end, right? And so our Gaussian surface, we're going to have a sphere again. And so if we want, we can say this has some charge Q. And so the first thing I like to do is figure out what Q enclosed is going to be. And for this, it's just Q, right? Now, we're going to have more exotic problems in the future where maybe instead of a point charge in there, we have some sphere that has some charge density rho, which is going to be coulombs per meters cubed. And you know, you have to multiply by the volume of your sphere to find the total charge, but we're not going to start with that. All right, we'll save that for when we get to it, by definition of how time works. Okay, so we have Q enclosed, and then we want to look at E dot dA, right? And so, as we said, the area vector is going to be pointing out. We have the electric field vector pointing out. We go over here. It's this, excuse me. It's the same story, right? And so we have E is parallel to dA along entire surface. We'll also go ahead and say our surface has some radius r, and then we should be good to go. And so since E is parallel along the entire surface, then we have just E dA. Since the electric field we're at the same distance away from it everywhere, right? R is a constant here. We can go ahead and pull this out. Which is just going to be E times A, where this is 4 pi r squared. And so we go ahead and plug this into Gauss's law, right? We said this entire thing, including the integration, is 4 pi r squared. And so we go ahead and plug all this in. We get epsilon naught times 4 pi r squared is equal to Q. Well, Q enclosed, so it was just Q. Drop the E, right? Epsilon naught E, right? I know they look similar. Let me clean this up a little bit. Right, and then if we want to rearrange and solve for E, we're going to divide by 4 pi r squared and epsilon naught, and we get E is equal to Q over 4 pi epsilon naught r squared, right? Which, yeah. And then we can say, hey, electric field has to be pointing radially outwards. So we get an r hat, we get the vector, and look at that. We have agreement. Right, and so that's the very basics of how to use Gauss's law. Right, and so we used Gauss's law to derive Coulomb's law. Right, which that's pretty fun, right? Well, Okay, now, I mean, technically Coulomb's law deals with the force. So let's make this technically correct. To derive the same E field of a point charge that we found via Coulomb's law. All right, which is pretty cool. It's always great when the physics is consistent, right? The things we did one way now work out the way something else did. Let's see what we want to go to next. We can talk about a conducting surface. Well, yeah, let's hit a cylinder real quick. So I think that's 23-7. All right, and so now let's say we have some line of charge, which we can say it has some charge density lambda, which is going to be charge per length. Okay. And so, as we briefly said, the electric field will be pointing straight out from all these charges. Okay. And so let's come along and bring in our Gaussian surface. I guess we'll keep using pink for that. And so all right, we have our Gaussian surface here. And so let's start off with Gauss's law once again. Okay. And let's go ahead and say our surface has some radius r and some height h. Well, so the first step, as we said, is to figure out Q enclosed. And so right now it's not quite so simple as just saying, hey, Q is Q. Right? And so Q enclosed, we're going to get lambda, our charge per length, times h. That's a jacked up looking h a little bit. Right? And so it's charge per length times length gives us charge. Right, as you can look at this picture, if we were to extend our Gaussian surface, right, infinite. Right, as we extend our surface, we encompass more charge, right? And so the charge enclosed is directly related to the height of our cylinder, which is, here's where things kind of start to get a little abstract, because the cylinder's not real, right? We just decided, hey, I'm going to draw this cylinder here, and we're going to get some height h from it. And so it's like, how is this going to come into play? But you'll see at the end, the h's are all going to cancel out. And so we have the right-hand side of Gauss's law figured out. So, yeah, sure, we'll do this in yellow. E dot dA. As we said, this is going to be equal to the surface integral of, you know, if we call this A1, A2, it's going to be 2 A1 dot D E dot dA1 plus E dot dA2. All right, and we said these are going to go to 0 because the electric field points straight out. None of it goes up or down, or the area vector, well, the area vector points out and up. Right here is the area vector points out on both sides, right, all around, right, symmetrically for a cylinder. And so we get this E dot dA is equal to just the integral of E dot dA2. Okay. And then we can also say, since these are going to be parallel, we have this. Since we're at a constant distance away from the charge distribution, E is going to be a constant. We pull that out. And the integral of just dA gives us EA. And so, right, we can't forget our epsilon naught. And so what we get on the left-hand side is epsilon naught EA. And we have that is equal to lambda H, the charge enclosed. And then if you'll remember, we had this equation for a cylinder, for the area of a cylinder. 2 pi RH. And so putting it all together, we get epsilon naught E times 2 pi RH is equal to lambda H. And look at that. H's cancel out as was foretold. And so if we want to solve for the electric field, we divide everything else out. And we have E is equal to lambda over 2 pi epsilon naught R. And so you might be wondering, whoa. We've always had an R squared in the denominator. Have we changed the units for electric field? And the answer is no, because we have lambda, which is charge per length. And so this here, right, instead of having a Q over R squared, we have a lambda over R. And so instead of charge per length squared, we have charge per length, right, which gives us charge per length squared again. All right, a little sanity check, just make sure the units are all beautiful. And so, yeah, just so we get E is equal to lambda over 2 pi epsilon naught R. And if we want, we can slap an R hat on there. Right, because we are always going to be pointing radially outwards from our line. Cool. And so those are two of the main symmetries for Gauss's law. We can go ahead and go to 23.8, and we have planar symmetry. And so let's say we have a sheet of charge. Yeah, my powers grow daily. All right, and so let's say we have some value sigma, which is going to be equal to charge per area. And then we're going to draw what is commonly referred to as the Gaussian pillbox. I guess people were taking a lot of pills back when Gauss was doing his thing. I don't know if that's true. What I do know is there used to be a thing called a pillbox, right? That was basically shaped like this. It's a cylinder, but then there's a hinge on here so that the top can open and you can have, you know, your I don't know why I'm drawing pills. Right, but your pills go there. It's a pillbox. It was a very common thing for people to carry back in the day. And as this equation came from back in the day, sometimes the terminology follows things, and we have the Gaussian pillbox. And so what that looks like is we're actually going to go to a side-on view and say, if here is our sheet, the Gaussian pillbox looks like this, right? And so, we kind of draw something that's going to be like that. It's hard to draw 3D things on a 2D surface, right? And so I guess we're going to investigate the side-on view for a bit. And so we have the electric field is going to be coming out everywhere, right? From the plane, it's just going to point straight out to the sides. And so this kind of looks like the cylindrical symmetry, but this is different, of course, because this sheet is extending in and out of the plane, whereas here we had this was just a line of charge. Right now it's a sheet, but we're looking at the side. And so if we look, we can see we have area vectors pointing out here, right? If we have some radius r, and so we can say we have A1, A2, and then I guess A3 for the sides of the cylinder. And we have the only now the A1 and A2 will survive. Right, so only the caps of the cylinder are going to survive the integral. And so let's start off with figuring out what Q enclosed is going to be. And so if this is R, we can say Q enclosed is going to be sigma, our charge per area, times 2 pi r squared, the area of our circle at the end of our cylinder. Okay, and so then what we get, and we look at the left-hand side, right, we're going to look at our integral, E dot dA. All right, let's just rewrite Gauss's law again, just so everyone has it. It's Q enclosed. And so we have our E dot dA. That's going to be equal to E dot dA1. I'm going to go ahead and say A2 is also A1 by symmetry, right? And then so we have plus E dot dA1 because we hit them on both sides. And then plus E dot dA3, which of course will go to 0 because there's no point along A3 that has any flux. And so we get this left-hand side is going to become, well, so the dot products are going to be parallel, and so this goes to EA, and so we have the integral of 2E dA. And so let's see, we're going to go ahead and pull out a 2E, and we get this is equal to 2E times the integral dA, which is equal to 2E times A. And hey, if we really want to, we can just call this area A, and we can say Q enclosed is just sigma A, right? We don't even need to worry what it is for this problem. And so then we plug all this into the left-hand side. We get our epsilon naught times 2EA is equal to sigma A. Area cancels out, right? And so, hopefully you're starting to kind of notice the game of this is that we pick some arbitrary shape to be the surface that we're going to look at the flux through. And then typically most of the parameters of that shape end up going away, right? Right, you always have an R just because the electric field depends on R, and so that has to stay in there. But the height of the cylinder, the area of the pillbox, all goes away. And so if we want, we can say E is equal to sigma over 2 epsilon naught. Okay, which interesting result, right? Does not depend on R. right? Which I know I was just saying that the electric field depends on R, but this one's a little funny because imagine you have an infinite wall of something and you're some distance away. As you get closer, it's not going to look any bigger, right? Because it's already infinite. If you get further away, it doesn't look smaller. And so the electric field, due to an infinite sheet, is going to be constant everywhere, just because of the nature of infinity. Right, and so that's a fun result that we get. And I think we're going to go through and just do 2 conducting plates real quick. And so if we want to go ahead and draw our 2 plates, right, we could have one of the plates be positive, one of the plates be negative. And if we look at the electric field, some sigma 1, well, negative sigma 1, I guess, Right, and so just by the nature of conductors, you're going to have the same surface charge density on both sides of the plate. I guess if we want to be really good about this, which of course we do, we would put plus, 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 right? Because the charge builds up on the surface. And of course, the charge builds up on the surface of conductors, right? Like charges repel, so they want to get as far away from each other as they can. They're in a conductor, so they're free to move. And so if you picture a sphere is probably the easiest way to picture this. Actually, we just do a circle, right? If we were to put 4 charges in here, right, they're too close. They're going to try to go as far away from each other as they can, and we end up with the 4 charges on the surface, right? And so that's the general reasoning behind why you always have, in a conductor, all of the excess charge only lives on the surface. And so here, if we have the conducting plates, we get that these are going to have electric fields going out. Plate 2 is negative, so electric fields point in. And so let's kind of look at what happens. And as we discussed, it's infinite. These electric fields are constant as far as we go. So even if we go back all the way to the other side, this electric field is still going to be pointing in with the same magnitude. And we can see these are going to cancel. And you're going to get something very similar here, right? You have the electric field going this way. These cancel. If we want to go the opposite way, over here, we're going to have an electric field going this way. These cancel. And so what you get is no electric field outside the plates, but you get 2E inside the plates because they're all pointing in the same direction. Okay? And so you get E is equal to 2 sigma 1 over E naught. And then here what we did is if you have the same overall sigma that we had here, here since we just had a 1D plate, we only had we had a 2D plate, right? There was no thickness, it only had one side as opposed to 2 sides. So all these charges built up on only one side. And so if we go back to the electric field we had or the sigma we had before, we can say sigma 1 is equal to 1/2 sigma from this sigma. And so we get E is just sigma over E naught, as opposed to having the 1/2 in there. And I think we'll wrap it up there for now, and we'll do some practice problems soon. Let's wrap up Gauss's law real quick with spherical symmetry. So what we're going to try to do is use Gauss's law to verify the shell theorems. Okay, the first shell theorem says that if we are outside the shell, treat it as a point particle. And the second of the shell theorems says if inside a uniform shell of charge, no E field, or force, right? And so let's get started. And so let's say we have, right, some ring of charge. I don't know what's going on there. All right, let's say there's a bunch of charge all distributed in this kind of a uniform thin shell, right? So I'm drawing it as a two-dimensional thing, but imagine this is 3D. And let's say this is all located at some distance r away from the origin. Let's say you have some inner surface S1, outer surface S2. Let's say there's a net charge Q. And actually for S1 and S2, we'll have those be... That's the worst circle I've ever seen. Okay, and so S2 is that surface, S1 is this surface. Okay, and then let's say we have some R that we can vary, right? And so we're going to look at when R is less than big R and R is greater than big R. And so let's start with R is greater than or equal to capital R. Okay? And let's see what we get. Q enclosed is just Q, right? And so let's look at the left-hand side of Gauss's law. Epsilon naught integral E dot dA. And let's go ahead and draw our Gaussian surface, right? And so we're at some value R greater than big R. And so we're going to use S2 as our Gaussian surface, right? And so, right, imagine that this is a sphere. And, well, let's look and see what the field lines we expect from this charge distribution. Let's say all these charges are positive, so the field lines point out. That's kind of always easiest to visualize. Okay, so pointing radially outwards. Let's see what the area vector is going to be doing. Wow, it also will point radially outwards. Okay, so since these are going to be parallel, you know, we can say E dot dA is equal to just E dA. If you wanted to, you could rewrite this as E dA cosine theta, where theta is equal to 0, so cosine goes to 1, and you just get the E dA, right? There's a couple different ways you can look at this and justify it. But we're just going to go ahead and say EDA. Then our surface S2 is taking advantage of the symmetry of this problem, such that every point along the surface, if you know it was drawn better, would be equidistant from this shell of charge. If we're at the same distance from the charge, then we expect E to be a constant, and so we can pull it out of this. And so we got epsilon naught surface integral EDA is equal to epsilon naught E times dA. Integral of dA is just going to be A. And the area of a sphere is 4 pi r squared. Okay, and so the left-hand side of Gauss's law turns into E times 4 pi epsilon naught r squared. Right, and I kind of moved the epsilon naught around a bit just so we have that 4 pi epsilon naught that we see everywhere. And this is where that comes from. This is why we see it everywhere. Because everything has, not everything, most things dealing with like a charge has a spherical symmetry, right? Anytime you have a point particle and you have a field that goes out radially, you get a spherical symmetry, and the area of a sphere gets the 4 pi r squared. And so when we have 4 pi epsilon naught r squared, that looks like a 3 almost. That's where that keeps coming from. Cool. And we'll call this star. Well, I guess this one should be star, and this will be double star. And then we just set star, well, we'll do double star equal to star. And so we have E times 4 pi epsilon naught r squared is equal to Q. Solving for E. Wait, how in the world did that line just come out of nowhere? And so we get E is equal to Q over 4 pi epsilon naught r squared. And if we want, we already decided this was going to go in the r hat direction. And wow, look at that. That's the exact same as the electric field due to a point particle. So we found the same electric field as with a point particle at charge Q. You know what? This deserves an exclamation point, not a period, right? This is a wonderful result. And so yeah, hopefully that kind of validated the first of the shell theorems. And now let's go for R is less than big R. And so we're going to look at S1. And so let's say S1 is this surface here. Well, Q enclosed is 0. So therefore the electric field is 0. Right? If we look at the left-hand side, epsilon naught E dot dA is just equal to epsilon naught EA. And so the area has, 4 pi r squared. Epsilon naught's not 0. That's equal to Q enclosed, which is 0. So the only way this works out is if the electric field is 0. And there we go. We have validated both the shell theorems. Okay, let's do something maybe slightly more interesting. Let's say our charge distribution is still going to be uniform, but let's say it's not just like a thin shell. Let's say maybe it's a volume thing. This one was out of line. I got me. All right, and so maybe this is all some charge with a total charge Q. Flying a little too close to the sun. Once we can imagine electric field lines are all going to go radially outwards. A little messed up arrow. Okay, and so let's say we want, well, let's say this has some radius r. And let's say we want to look at the electric field for r is less than r, right? And so we're going to have some Gaussian surface, some length r. It's a sphere, so we're going to do a spherical surface. And let's try to figure this one out. Well, left-hand side's pretty easy. Right, so let's see. Our area vectors would be pointing out like this everywhere. Oh, wow, they're parallel to electric field. So this dot product goes away. We use the symmetry creatively, so the electric field will be constant everywhere on the surface, so we can pull that out of the integral. Integral of dA is just a. We get epsilon naught EA. Wow. Anyone noticing a pattern starting to form? Hopefully. And so we'll call this star. Well, we can go ahead and not do that yet. Go ahead and not do that. All right. All right. Area, 4 pi r squared. So the entire left-hand side we'll have goes to E times 4 pi epsilon naught r squared. All right. Shouldn't be too shocking of a result, right? It should be a little familiar at this point. And so let's find charge enclosed. Well, if it's uniformly distributed, we need to find the fraction of the volume we are occupying with our Gaussian surface, right? If we had our Gaussian surface occupying the whole sphere of charge, then we would just have Q. But we're going to have Q times the volume of our Gaussian surface divided by the total volume, right? The volume fraction we occupy is the volume fraction of charge we get, right? Because it's uniformly distributed. And so we can say that's going to be equal to Q times 4/3 pi. Our Gaussian surface has a radius little r, so we can go little r cubed divided by 4/3 pi. This had a total surface of capital R cubed. And look at that. We can cancel out the 4 pi. And so we get Q enclosed is equal to Q, the total charge of the whole sphere, times little r cubed over big R cubed, because of the volume fractions. Okay, so we're working with something here. We'll call this equation double star. And then we're going to set equation star equal to equation double star because they're the two sides of Gauss's law. And so we have E times 4 pi epsilon naught r squared equal to Q times little r cubed over big R cubed. Well, off the rip, I'm going to get rid of that r squared and turn the r cubed into just an r. And then go ahead and solve for E. E is equal to Q over 4 pi epsilon naught r cubed, and then an r up top. And so that's the electric field for little r is less than or equal to big R. And I encourage you to see what happens when little r is equal to r. See what we get, and see if that makes sense from the shell theorem. I'll leave that as an exercise for y'all to do. Okay. So there's that. Let's hop into a practice problem. And so I'm going to say epsilon naught is 8.85 times 10 to the negative 12 farads per meter. Probably going to come in handy. And so we have the drum of a photocopying machine has a length of 42 centimeters and a diameter of 12. Okay, if the diameter is 12, the radius is 6 centimeters. So I'll go ahead and put the height was 42 centimeters. And we're given an electric field equal to 2.3 times 10 to the 5th newtons per coulomb. And what is the total charge on the drum? All right, let's go ahead and draw this. So we have a bunch of charges all over this, kind of uniformly spread out. All right, if the charges are all over the surface, we're going to expect to have electric field lines pointing out. So let's see. Our Gaussian surface, probably going to be a cylinder. And since it says the electric field line just above the drum surface, we're going to have our Gaussian surface be the same as the drum. Just like we kind of had set up here, that you could have your Gaussian surface be equal to the size of the thing. And so that's what we're going to do here. And so we're looking for Q. So let's start with Gauss's law. Right. Okay, so we have our Gauss's law. We're looking for Q enclosed, so it's already arranged for what we need. And so then the left-hand side is going to do the usual thing where we have, it's going to turn into epsilon naught E times A, where A is going to be 2 pi RH. And so we get Q enclosed is epsilon naught E times 2 pi RH. Or Q enclosed is 8.85 times 10 to the negative 12 farads per meter times E, which was given to be 2.3 times 10 to the 5th newtons per coulomb times R, 0.06 meters, times H, 0.42 meters. We go ahead and we plug all this in. And we get probably like an answer. Yeah. And we get Q enclosed is equal to, well, I'll just do it down here. 3.2, oh, nope, times 10 to the negative 7 coulombs. Okay, cool. Right, so not a lot of charge, but a whole lot of electrons. Okay, so then let's do B. The manufacturer wishes to produce a desktop version of this machine. I'm sure you all have one on your desk at home, a photocopying machine. And so the drum length is going to go to 28 centimeters, 0.28 meters. And it says the diameter goes to 8 centimeters, which means the radius goes to 4. And the electric field stays the same. And we want to know the charge. Right? Yeah, so the electric field can't change, and so now we need to find the charge on the drum. And, well, it looks like we can use the same equation, just plug in for these. Oh my goodness, I forgot to write the 2 pi. I had it in Desmos, so the answer is good. Times 2 pi times 0.04 meters times 0.28 meters. I could just make the paper wider. That's what a time to be alive. And so we get Q enclosed is going to be equal to 1.4 times 10 to the negative 7 coulombs. And let's see, does this make sense? Well, we have a lower charge. We use the same equation, but we lowered 2 of the things we're putting in there. So yeah, I'd say this makes a good bit of sense. Okay, so that was a one-dotter, relatively straightforward problem. Let's go to something a bit more complicated here. First, we're not doing 53 yet. We can maybe do that in class or something. And so we have a spherical shell with uniform volume charge density rho is 1.84 nanocoulombs per meter cubed. Go ahead and write that down. Nanocoulombs, so 10 to the negative 9 per meter cubed, right? So already we're going to have to multiply by volume to get charge. And so just, always good to, as you're doing these problems, when you see things, go, okay, like, what am I going to need? How am I going to use this to get there? And so it's already have, a plan starting to form. And so we're given A is equal to 0.1 meters, B is equal to 2A. And let's go ahead and get started. And so, well, to start, let's draw some pictures. Let's see, charge is yellow. Okay, and so we'll slap that with the rho is equal to 1.84 times 10 to the negative 9 coulombs per meter cubed. We can go ahead and have the electric fields going out. Right, this is what we expect the electric field to look like. So when we're drawing some surfaces later, it might be a little easier. We can go ahead and say this distance here is A, this distance here is B. Right, off to a pretty good start. And so let's see what part A is asking for. Well, it looks like we're always looking for electric fields. We're always looking for the magnitude of electric fields. At r equals 0. Well, first step in any Gauss Law problem is to identify the symmetry and draw your Gaussian surface. Here we have spherical symmetry, so we're going to be drawing spheres. Okay. At r equals 0, well, you can't really draw much of a sphere there. And so we have Q enclosed is equal to 0, and also the area is 0. And so we're going to have the electric field is equal to 0. Right? If we go epsilon, well, we can skip the area equals 0 part, because let's say it's an infinitesimal area, right? We have a small amount of area. E dot dA is equal to epsilon naught EA is equal to 0. And we get 0 equals 0, the electric field is 0. Right? Okay. And that's all you have to do for A. B, we have R is equal to A over 2. And so now maybe our Gaussian surface is doing something like this. Oh, look at that. There's no charge enclosed. The electric field is 0. C, though, we have R is equal to A, no charge enclosed. The electric field is 0. This is the rest of the class. Just everything is 0. No, that'd be a really boring class. Right? Who wants to do something because it's easy? Like, salmon don't swim upstream because it's easy. They do it because there's a result. Sure. So at D, we have R is equal to 1.5A. And so our Gaussian surface is going to be somewhere out here. Maybe clean some of this up a little bit. You're gone, you're gone, you're gone. Cool. And so we can have this be our Gaussian surface. And so now we have some charge enclosed, so we have to actually start doing some stuff. Oh, that was for R is equal to A. Okay, so let's try to figure out how much charge enclosed we have. Okay. Well, let's first start and just say, like, what if we look at how much charge total there is? right? We're going to say if there's rho, it gets us to some total charge Q. And so Q is going to be equal to rho times, well, if it was a solid sphere, it would be just the volume of the whole sphere, right? If we had something like this, and it had some rho, and it had some r, then it would just be rho times volume gets you charge, right? Because rho is charge per volume. But here what we have, I don't know what that was, is we have all the charge in an outer sphere, and then we have kind of a hollow core. And so if we have to multiply by the volume occupied by this charge, what we would do is have this be the total volume minus the volume of that hollow core. Okay. And so you would have, now if we go back to our picture, we would have like VB minus VA for the total charge. And so we would have something like 4/3 pi B cubed minus 4/3 pi A cubed. All times rho. And that'll give us the total charge of this setup. But we're not that far, right? We're halfway through A and B. And so what we're going to do is we're going to say Q enclosed is equal to rho times 4/3 pi r cubed, which is 1.5 a cubed, minus 4/3 pi a cubed, right? Our Gaussian surface is located at r is equal to 1.5 a away, and so it has a volume 4/3 pi 1.5 cubed a cubed, right? All we did was took 1.5 a, cubed the whole thing. And then we subtract out this hollow core that we have here. Cool. Okay. And the reason we can ignore all the outer charge is because by one of the shell theorems, right, we have a uniform shell of charge outside of what we're looking at. It has no contribution to the electric field because it's outside of our Gaussian surface. And symmetry. Okay. And so now we have this, which we can kind of clean up a little bit, is equal to rho times 4/3 pi a cubed times 1.5 cubed minus 1 cubed, right? Because we pulled out a 4/3 pi a cubed, and pulling that out from itself leaves a 1. Oh, so I guess we don't need to cube this because typically when I do it, I leave the a there. Right, but 1 cubed anyways is just 1, right? Yeah, so I was thinking we pull out an a from, no, all right, whatever. And we get this as our total charge. And so we can go ahead and label this, we'll call this equation double star. And then if we want, we can look at the left-hand side, epsilon naught surface integral E dot dA. Well, let's look at what we got going on here. Let's see, the area vector is going to point radially outwards. Oh, wow, that's parallel to the electric field. So we can get rid of our dot product. Let's see, since we chose a convenient symmetry, electric field is going to be constant. We can pull that out. Integral of dA is just a. And we are at some distance r. And so we have 4 pi r squared. but r is 1.5a. So we are going to make this 1.5 squared a squared, and that's our r squared, right? And so we get the left-hand side of Gauss's law goes to e times 4 pi epsilon naught 1.5 squared a squared. We can call this equation star. And then we want to set star equal to double star. All right, you can use 1s and 2s to identify your equations. I started using stars in undergrad and just never looked back. Okay, so let's move e times 4 pi epsilon naught 1.5 squared a squared is equal to double star. So we have rho over 4/3 pi a cubed times 1.5 cubed minus 1. Let's clean this up a little bit. 4 pi a squared. Can get rid of the cube. And you know, I like to do a different amount of dashes for each thing canceled out, which is, again, a habit I started in undergrad. Right now I have more colors at my disposal, so I guess I very easily could have just done, now this is green, this is yellow, right? Just a way that, like, if I make a mistake, it's easy to identify what went wrong, right? Right, just a little tip, I guess. And so we have E is equal to rho A times 1.5 cubed minus 1 over 3 epsilon naught times 1.5 squared. What is this? This is part D. Yeah, and so we can go ahead and start plugging things in. 1.84 times 10 to the negative 9 coulombs per meter cubed times 0.1 meters times 1.5 cubed minus 1. 8.85 times 10 to the negative 12 farads per meter times 1.5 squared. Okay, and when we go ahead and plug all this in, we get E is equal to 7.32 newtons per coulomb. Okay, and so there's part D. E is asking us R is equal to B. Okay, so let's see the left-hand side. So 4 pi b squared, but b is 2a, so that gives us a 4a squared. Right, and so once you start getting comfortable, you can kind of speed things up a bit, right? I didn't go through the whole, oh, well, the dot product goes away, then we pull the E out, and then this is that. It's just like, I know this is going to be that. Cool. And so let's see, Q enclosed is going to be, well, for Gaussian surface, is now at B. Oh, we get all the charge. Okay. And so we can say Q enclosed is just rho VB minus VA. All right, and so that's the total volume minus the hollow core once again. And so we can say it's rho times 4/3 pi b cubed. Well, b is 2a, so 2 cubed gives us an 8a cubed and then minus 4/3 pi a cubed. So we can say rho times 4/3 pi a cubed times 8 minus 1, which is rho times 4/3 pi a cubed times 7. Look at that, we got a 7 out of some geometry. How rare is that? It's a good day. And so we'll call this star star, and we set star equal to star star. And we get epsilon naught e times 4 pi times 4a squared. Right, and I didn't multiply the 4's together because I know we have a 4 pi on the other side that's going to cancel out. Then a 7. Like, that just looks so out of place to me. Let's see, 4 pi, a squared, get rid of the cube. I believe that's all the canceling we do. Yep. And so we have E is equal to 7 rho times A over 12 epsilon naught. Right, 12 because we have a 4 and a 3. Right, we're dividing that. It gets down there. Cool beans. And so we can say this is equal to 7 times 0.1 meters from the A times 1.84 times 10 to the negative 9 coulombs per meter cubed. And 12 times 8.85 times 10 to the negative 12 farads per meter. And we get plug all this into Desmos, and we get 12.1 newtons per coulomb. And then we can write our answer a little nicer so we can box it up, right? And so we get E is equal to 12.1 newtons per coulomb. And if you want, you can specify this is where R is equal to B. So A, B, C, D, E, F comes next. That's the alphabet we all know and love. R is equal to 3B. Whoa. Well, let's take a look at this. So now our R is 3B, right? Not to scale. Q enclosed is still just the total charge. And so we get Q enclosed is going to be rho times, well, realistically, right, it's going to be this. Why would you do that? Oh, it made a line that went all the way. That's fun. Wow. Thanks for doing that. And so if we look at this, it's still the total charge. So we can just jump straight to this if we want. And so it's going to be equal to rho times that 4 pi over 3 a cubed, and then our 7 is still there. Okay, and we'll call this equation double star still. And then on the left-hand side, we have our epsilon naught integral E dot dA is equal to epsilon naught EA. And here, A is going to be 4 pi R squared. R is 3B. B is 2A. So R is 6A. So R squared is 36A squared. And so we get the left-hand side turns into epsilon naught E times 4 pi 36A squared. And we set that equal to double star, which is rho times 4 pi over 3A cubed times 7. Actually, before we go further, let's see. So both E and F, both have all the charge enclosed. So you might kind of think, oh, we're going to get the same electric field. but we're further away from the charge. So we should be getting a lower electric field, which we can see, you know, if we continue our field lines out to the point where they hit our new Gaussian surface. Right before, let's pick a new color, it's pink. Right, we're pretty close together in our field lines. Now they're further away. We're further away from the charge. Our electric field lines are more spread out. Everything is telling me, hey, we're about to get a lower electric field. And so let's see if that's the case. Well, 4 pi. A squared and a cubed leaves us with an A. And so we get E is equal to rho A over epsilon naught times 7 over 3 times 36. Right? Epsilon naught E, the 36 is there, the rho is there, 3A7. Yep. And so 1.84 times 10 to the negative 9. Nope. Coulombs per meter cubed times A, which is 0.1 meters, over 8.85 times 10 to the negative 12 farads per meter, times 3 times 36. And when we plug all of that into Desmos, you get E is equal to 1.35 newtons per coulomb. All right, and so that is, in fact, less than 12.1 newtons per coulomb, as we expected. Okay, well, thanks for watching. Hope everyone followed along, made sense. Ask me if you have any questions, and